Hey guys, welcome back to Genius Learning. Here we have another problem dealing with dielectrics in a sphere. And before we start, let's be clear about what's going on here. We got two layers of dielectric, the blue and the orange, denoted by KE1, KE2. And then here we have the radius of R naught goes to the space between the two dielectrics, all right? And here is the same picture but opened up in the middle, kind of like sliced in the middle. And we could see that A radius goes to the empty shell in the inside, right? That has a charge Q. And then B goes all the way to the outside, which is past the outer dielectric. Okay, so R naught is in between them. There's positive charge on the inside, negative charge on the outside. And anything else? I think that's it. So these are the bounds. So KE1, which is this one, exists between A, which is up to here, and then R naught, which is here. So it's only that orange spot. K2 is R naught all the way to B. All right, so there's a limit. So now we're asked to find the capacitance of the system by finding the total energy of the fields between the plates. So we're asked to find the capacitance in a specific way. All right, and let's look at the equation that relates the two. So we got total energy, okay, is equal to Q squared over 2C, and that C is for capacitance. Okay, and so with this equation here, rearranging it, we see that we got C is equal to Q squared, charge squared, over 2 total energy. So this is what we're ultimately looking for, the capacitance of this system, and by finding the total energy. All right, so let's start off with Gauss's law. All right, so if we take a look at all the equations that can lead us to getting the energy, we're gonna find that we'll need electric displacement. All right, so let's write it right here. So we're gonna use Gauss's law for electric displacement, dotted with dA, Q free, enclosed. All right, and let's see, we'll box that up. Okay, so here on the left side, we're gonna have two integrals. Okay, 0 to 2 pi, 0 to pi, and then our displacement vector, we're gonna have the Jacobian r squared sine theta, d theta, d phi. All right, and that's gonna equal Q free enclosed. The only thing that's gonna be free and enclosed is just gonna be the Q by itself. All right, and we're gonna use that for the general term, and that's the only thing that we have available, Q. Okay, so now solving this side, we're gonna get d 4 pi r squared equal to Q, and displacement vector is gonna be Q over 4 pi r squared in the radial direction. Okay, so we have that, and now let's see why we needed our electric displacement. Okay, so moving on to the next part, we're gonna need, where should I write it? Okay, maybe I'll put it down here, and we'll move to the side here. Okay, so I'm gonna put here the equation we're gonna need for total energy. So remember that when you see total, think of integrating, because integrating will give you the total of something, especially if there's like a limit or a length that we want to go up to. And so the total energy is going to be the integral over all space. And we got lowercase u e, which is energy density, d tau. So that's a volume integral. We're going to need this equation, right? Because we need the total energy to put in here to get our capacitance, right? And we need electric displacement because inside of energy density, we can represent this u in 3 different ways. Okay, we're definitely only going to pick one, but let's just show the 3 equations we could pick. So ue is equal to 1/2. We got d times e. We got energy density is also equal to 1/2 epsilon electric field squared, or energy density is also equal to displacement vector over 2 epsilon. Right, so that's 3 possibilities depending on what we have, right? That's what's going to be dependent on which one we use. Okay, so let's label this 1, 2, or 3. So we got to this part here where we're going to integrate over all space, right, for total energy, but the energy density can be expressed in any one of these ways and then put in here. So since we found the electric displacement, then I'm going to go with this one here, the bottom one. So let's choose this one down here, and I'm going to write it. So now let's go from here, let's go over here. Okay, our UE with electric displacement of Q over, and remember that the D is squared, so we're going to have Q squared over, this squared is going to be 16. 16 times the 2 on the bottom here is going to be 32. Okay, I'm going to have pi squared, and I'm going to have r to the 4th, because it's squared right now, and we're squaring it, and then we have epsilon. Okay, and this right here is a general notation, right? So it's a general notation because we have epsilon, and this doesn't describe the susceptibility of the material. So we have to identify where we're at inside of this material. We could be inside the orange part, we could be inside the blue part. Okay, so the next move from here is to separate this into the different parts that we could possibly exist in. So let's write down the equation first, and let's remember that. I'll write it down over here. Okay, epsilon is equal to dielectric constant times epsilon naught. Okay, and let's see what we get for this part here. We're gonna split this into 2. So we got for A less than or equal to R less than R naught. So our R is right here in between the A and the R naught. For that dielectric constant, we're gonna have UE equal Q squared over 32 pi squared. And now what changes down here, let's keep the R 4th, right? The only thing that changes is this expression. We need to express what area we're in by saying what the dielectric constant is in the location where we're at. Okay, so this changes into this, but more specifically, instead of this staying as KE, we're in the region where KE1 exists. So we have KE1 epsilon naught. So that's very specific, and that needs to be noted. So this is the general form, and now you can see that specifically where we're in this region, this is our energy density, and then you can kind of already see that for the next region, we're gonna have the same thing, but with 2 here. So our energy density is gonna be 32 pi squared r to the 4th Ke for the region where you're between R naught and B, which is here. You have dielectric constant Ke2, and then epsilon naught. All right, so 2 different energy densities, 2 different regions, right, with 2 different dielectrics. And so that's the answer for the 2 regions that we're in. So this is not the answer, this is just the general form. We need to divide this into 2, and now this is the proper expression for energy density. And we need energy density for identifying the total energy of the system, right? So since we need to integrate over all space, we need the energy density of both regions. And now let's look for the total energy. All right, so again, let's move up here and use a different color here. Let's see. All right, so now let's look at total energy, okay, over all space. First, let's look at U, capital U, E1, okay? And I should label these 2 here. I should label them. This is E1, this will be E2, right? Corresponding to the dielectric that they're in. So the total energy, E1, we're gonna have 3 integrals. Okay, the first 2 are always the same for a sphere, and here is the tricky part. So now we're gonna use E1, right? And the region where this one exists is between A and R naught. So that's what we're gonna put here. We're in this region right now, and in this region, the energy density is this right here. Okay, so let's write that. Q squared over 32 pi squared r to the 4th Ke1 epsilon naught. And then we have the Jacobian r squared sine theta dr d theta d phi. Okay, so let's make sure we're good. Okay, so now let's evaluate this integral. All right, this represents the total energy of just this dielectric. Let's see, we got the solid angle, let's take that out, 4 pi. We could take the Q squared out. Ooh, ugly Q. Q squared, okay, we got 32 on the bottom, we got pi squared. This r to the 4th and this r to the 2nd, so this one gets canceled, and down here turns into a 2. We could take out the Ke1 and the epsilon naught, and all we're left with is the integral from A to R naught of r to the 2nd on the bottom. So I'm going to bring it to the top as a negative, and then dr, right? Okay, so then just evaluating this integral, let's see, we have negative 1 over r, evaluated from A to R naught, and let's see, just this integral here is going to be negative 1 over R naught minus a minus, so plus 1 over A. So this is the answer for this integral, and let's combine it with everything now. Okay, so we're going to combine it now, and we're going to say that the total energy in this region is going to be, let's see how we simplify. This is going to be 8 Q squared is gonna stay on top. We're gonna have 8. One of these pi's cancel with one of those. Okay, KE1 stays, epsilon naught stays, and then here stays the same. Let's just write it the positive one first. So we got 1 over A minus 1 over R naught. Okay, and this is the total energy for only this region here, the orange. Okay, so now let's get the total energy for the second region. All right, let's okay, so we're gonna do uppercase E2. So total energy, and this is in the region where the dielectric constant is E2. That's from R naught to B. Okay, so again, we got 3 integrals, 0 to 2 pi, 0 to pi, and we got R naught to B. Okay, and then the energy density in that region, we got Q squared over 32 pi squared R to the 4th KE2 epsilon naught. All right, we got the Jacobian R squared sine theta dr d theta d phi. Let's evaluate like that one. We got capital U. Okay, we got solid angle comes out Q squared. This Q's ugly. Okay, Q squared over 32 pi squared KE2 epsilon naught. One of these R's cancel, two of the R's cancel, so 2 and the bottom stays as 2. So we're gonna integrate R naught to B of R to the negative 2 because the R2 is on the bottom, dr. Okay. I think we're gonna have the same situation there. So let's solve it on the side here. So this integral by itself is gonna be negative 1 over R with the bounds B and R naught. And then that by itself is gonna be negative 1 over B minus a minus, so 1 over R naught. Okay, so now let's put this combined with all this constant here that we took out. So capital U E2 is equal to the same thing. This is gonna cancel, be 8, one of the pi's cancel. We got Q squared on top, 8 pi KE2 epsilon naught, and we got 1 over, we're just gonna rearrange this, write this in the front, 1 over R naught minus 1 over B. All right, so now we got the total energy in the second region where you have the energy density for this dielectric. Okay, so now that we have these two, right, we have the energy total because we just add them up. And so let's see. Now the energy total, let's write total on the bottom, is gonna be capital E1 plus capital E2. Okay, so since these are the totals already, then we can just add them up, stacking up the layers, and let's see what we get. We're gonna have UE total is equal to, let's see what they both have in common so we don't have to write so much. We got Q8 pi and epsilon naught. So I'm gonna pull out a Q squared over 8 pi epsilon naught. Okay, and this one has KE1, this one has KE2. So if I distribute this KE1 into here, I'm gonna have let's see. I'm gonna have 1 over A KE1, and then if I distribute it into there, I'm gonna have minus 1 over R naught KE1. So that takes care of the top one. Down here, I took everything out except for the KE2. So I'm gonna distribute that into the first one. I'm gonna get plus 1 over R naught KE2. And then distribute it into the second one, I'm gonna get minus 1 over B KE2. And that's it. That's our total energy. But we have one more thing to do. Okay, so this is now our total energy of the system, and specifically the question asks us to find the capacitance of the system using the total energy between the fields or between the plates. Okay, so we got the total energy, and now let's plug this into here and see what cancels out. All right, so for the last part, let's use, here we go. Okay, we got, let's see what the easiest way. Okay, we got C is equal to Q squared over 2. Okay, and this entire thing is on the bottom here. Okay, so let's try something. I don't want to do so much moving around. I'm gonna label this entire thing here alpha for now. So all I really have is, let me write it here. I have U total, uppercase U, right? UE total is gonna equal Q squared alpha over 8 pi epsilon naught. Okay, I'm just trying to simplify things. So I'm gonna make all this equal to alpha right now. And so alpha is gonna go on the top, right? Just rewriting it. Now let's put this under here and let's see if that helps. So I'm gonna have C is equal to Q squared over 2, and the U, which is, I'm gonna put UE total, right? The same thing. It's gonna be this. So I'm gonna write Q squared alpha over 8 pi epsilon naught. Looks a little cleaner. All right, and so if we really want to do it in like one more step, okay, so we'll do it in one more step. So we got C is equal to Q squared over 2, and I'm gonna flip this bottom here up. So let's already make that 4. So this doesn't exist here. We're gonna make that 4 already. All right, we're just gonna simplify this real quick. I'm gonna flip this fraction up to the top, and I'm gonna have 4 pi epsilon naught over Q squared alpha. Okay, so this 4 doesn't exist here because I took it from down here, 4 pi epsilon naught, to the top. Okay, so this is what we have left, this situation here. This Q squared cancels out, and this is what we're left with. 4 pi epsilon naught over alpha, but we know alpha is this entire thing right here. So let me just move this up a little bit and just write out the final answer. Okay. Let's erase this. All right, so let's write out the final answer. So we have here C is equal to 4 pi epsilon naught, right? That's what's on top. And underneath we have alpha, which we labeled this entire thing. Let's write it out. 1 over A K1 minus 1 over R naught K1 plus 1 over R naught K2 minus 1 over B Ke2. All right, and let's make sure you can see that. Perfect. So this is the capacitance using the total energy between the plates. Okay, don't get this general form confused. I know that this sometimes seems confusing, but try to see that the energy density matters if there's two areas that are different. This has a certain energy density, this has a certain energy density. How the electric, potential moves through here is going to be different because some dielectrics are stronger than others. And so these are very important. These, in combination with all space, right? So the total energy is going to be added up right here. And then, simple formula for the capacitance that equates these two specifically. And we end up with our capacitance looking like this. All right. Thank you guys for listening. I hope it was helpful.